Hi, period 6 kids. I'm just starting off with period 1. Not going to be there for your class today. Period 1 just took their integration quiz. Hopefully you guys got those turned in to the sub. And you're just going to follow along with notes for us. Real fast, period 1 kids. I know we covered this yesterday, but period 6 I forgot to show it to them. The 3 extra basic rules they're supposed to be adding into their forever cards. So let me quickly zoom back to that, and then we'll come right back to where we were. Period 6 kids, here we go. I know that we had that long old list, and if anyone was absent yesterday, you need to hear this too. We had that big old long list of, ¿Dónde está? Nope, before that. Basic rules of integration, before all of our practice problems, and there were tons of them. The problem is, our book has 3 extra. There they are. Our book has 3 extra. Don't worry, the extra stuff I wrote down on this page was me just showing where the formulas come from. But period 6 kids, there is going to be another forever number 32. You are going to see these rules in action a little bit, or you did see these rules in action a little bit on homework number 25. So I just wanted to make sure that you guys got them in your notes and most importantly in your forever cards at some point this weekend when I'm bored and chilling. Yeah. I will get them posted online so that way you guys have it, but I wanted to make sure you guys realize there were 3 extra rules we didn't write down. All right, everybody, let's go back to where we were, which is aquí. So, why was this stuff in section 4.1? Because now we can go from acceleration backwards. Physics people, or actually just common sense people. Every single motion problem that you could possibly think of, is it practical for acceleration of that motion problem to always be just a constant? Nope. The question is, can you always be on, well, that's not going to actually be a good. Cruise control acceleration is 0. I guess it would be constant. It would be 0 because you're not accelerating. So that one would be kind of weird, but is your foot always on the accelerator pedal at the exact same pressure and never changing? That's a little dangerous, right? Just a little bit. Anyway, so it's not very practical for acceleration to always be constant unless we're talking about, any physics people out there? What's an example where acceleration is always constant? Gravity. What? If you take a ball and you drop it, what makes it go towards the ground? Faster and faster. What do I mean faster and faster? What's the initial velocity of something that you're holding? 0. Now if you're throwing, if you're shooting, well, it's going to have an initial velocity when it leaves your hand, when it leaves the gun. However, if you're dropping, initial velocity is 0. So what on earth makes it hit and go splat if it was a raw egg? Gravity. And gravity is an acceleration, which is constant, roughly. That's for college physics. Anyway, coming back. Depending on where you are, gravity actually differs a little bit depending on your position on the earth. Interesting. Anyway, coming back. We say it's constant because we round it. If we are given a constant acceleration, which is the easiest example to work with, we can go ahead and integrate it as I'm about to show us where velocity functions come from and where position functions come from. Physics people, these are formulas you probably just saw and were like, oh, that's true, cool, I'll memorize it or I'll use it. Calculus people, nah, we understand where it came from. So, question kiddos, if acceleration is the rate of velocity, if acceleration is equal to velocity prime, how do we take a derivative and go backwards? We integrate. How do we integrate a constant? Pretend this is k. How do we integrate it? K times x, but we're not doing x's. Look at the little dt. Who are we doing? T, because in physics problem, motion problem, everything is dependent upon time. So we could say that velocity is equal to initial acceleration times time plus c when you have a constant acceleration problem. Ooh, this sounds almost like physics. However, there's something special with C. C is the constant of integration, and the special thing with C is, hey, guess what? If you plug in 0 for time, which means initially, what does C, plug in 0 for time. I said it and I didn't do it. Plugging in 0 for time. What's true about C? Who is he? Nope, that cancels out. He's the initial velocity, which we show as v sub naught. V sub 0, which is like v of 0, just a shorter way of writing. So we can actually say v of t for constant acceleration is equal to a sub naught t plus v sub naught. Physics people, that look familiar at all? Never mind. Just smile and nod. Okay, position function. How do we go? If velocity is equal to position prime. Period 6 people, we might have done a little bit of this yesterday, so it might just be review. If velocity is equal to position prime, question, how do we go back to position then? Given velocity. Integrate. So we're going to take the integral of a sub naught t plus v sub naught dt. Now, hold on. If a sub naught is just a constant, it's like kx. A sub naught t is like kx. Then question, how do you integrate? Separate them, do them one at a time. A sub naught is a constant, so he's just chilling. What do I do with t? I make him squared because he was to the first power, and what do I offset with my coefficient? I can do divided by 2 or do 1/2. 1/2 a sub naught t squared? That's like 1/2 gravity t squared. Plus, how do I integrate v sub naught, which is his own little constant like k? V sub naught times x, or t in this case, right? Plus c. Yeah, right? Now you know where they came from. X of t is equal to, those of you that haven't taken physics, this one's kind of important, in free fall models, right? What's so special about c? Well, guess what? If I plug in a 0, guess what happens to this first part? Guess what happens to the second part? So who is c? Not him, not him. C is the initial position. So x of t is equal to, putting it all together, 1/2 a sub naught t squared plus v sub naught t plus x sub naught. Oh my goodness. That's another important physics formula. Now, kiddos, in years past, I've actually had kiddos memorize this, but to be honest, on the AP, I've never seen them make you have these physics formulas memorized. It's more the understanding of how to get to velocity. Oh, I didn't write velocity, I apologize. How to get to velocity from constant acceleration, or actually from any acceleration function. We would just have to integrate. And how to get to position from any velocity. And wait a minute, what if you had an acceleration and you need position? How many integrals would you have to do? 2. Hey, in homework number 25, was there an f double prime given to you and you had to go backwards twice? What? That's practical. Okay, anyway. So this is the idea of why motion has returned. Because sometimes we start with acceleration like, hey, we know what gravity is in feet per second squared and meters per second squared. Or we can know what it is. Don't worry, non-physics people, you don't have to memorize these formulas. We're understanding how this works, not memorizing important formulas that show up a lot in physics. You also don't have to memorize gravity, even though it's a good life skill. But, anyway, coming on back. When you have something constant like gravity with a free fall model, we can go back to velocity, go back to position, and analyze each of those functions. Let's keep going. So technically, here we go. There is a forever card that I want you guys to know, but, didn't I just say I've never seen the AP actually test you guys on having these specific physics formulas memorized? So what am I saying? Fine, forget those. But I do want you to write down motion by integration formulas. We're adding to our motion arsenal, if you want to think about it that way. We've already written down a card about how to think about position, velocity, and acceleration by deriving. So similarly, we can also think about velocity and position and acceleration. Should have said those a little bit differently. With integrating. But remember, when you put plus c, if you have a specific clue, like the initial when time is 0, what the speed is, like in the dropped example, you could say initial velocity is 0. So we could plug and chug and find c, but that's kind of just like with integration. You can find c if you know a clue. You can find, see if you know a clue. So we're not going to necessarily write notes about that. Now guys, we might add to this forever card. There might be something else about motion I want you guys to write down, but for right now, we'll just say this is it. And I think this is forever card number 33. Okay. There might be more to come, but I don't want you guys to write down these physics formulas just because it might be useful in homework, but I've never seen the AP require you to have those memorized. They just want you to have the general idea. Sound good? Okay. A couple more seconds. And let's go see an example that's like what's going on in your book, homework number 26 that you're working on in class together tomorrow. If you can start it tonight, perfect. But you can work together tomorrow as well. Sound good? You guys got it? You don't have to write down the problem-solving steps because this is really any different than any other word problem you've ever seen. You read it, you figure out what you have, you draw a picture if it can help, you identify what you're supposed to find, and you go back through all of the things that you've learned in the past this year and in the years prior to solve it. Okay, let's forget that. Here we go. Example. This is actually directly out of our book, but sometimes it's a little bit better if I can explain it, and don't worry, I have a couple more examples for us to look at as well. And we're doing well on time. Solving a vertical motion problem. Vertical, which means up, down. So when velocity is positive, the ball's going up. When velocity is negative, the ball's going down. When acceleration is positive, it's being pushed up in a sense. Velocity is increasing, going up. When acceleration is negative, velocity is decreasing, which is weird, but that means becoming more negative, which means speeding up in the negative direction. Ooh, that gets confusing. We'll talk more about speeding up and slowing down, which isn't the same as velocity increasing and decreasing. Anyway, some of you caught that, some of you didn't. Here we go. A ball is thrown upward. Thrown upward. Ooh, so if it's thrown, it has, oh yeah, they say that. It has what? Sweet. So can't we go ahead, and if we're thinking about givens and find, can't we go ahead and say that our initial velocity is equal to 64 feet per second? Yeah? From an initial height. Ooh, what else do we know? Now hold on, this is dangerous in motion and in physics problems in general. We have to make sure that the units match, or else we have to do dimensional analysis building bridges. A question, whew, were they nice this time? Yes, if they said something like yards or miles, that'd be a struggle. But it's okay, dimensional analysis, you guys have done it before, you can do it again. All right, got it. Find, oops, letter A, find the position function giving the height s as a function of the time t. Wait a minute. All those formulas we just did, you started with an acceleration. Oh, they didn't give us an acceleration. Wait, it's going up and down. What's naturally the acceleration? Gravity. They didn't tell us what it is. Okay, we're going to write that down in a second, but let's go ahead and get it right now. My physics people, help us out. What's gravity, which is initial acceleration in these units? Nope. Nobody? Where are you guys? Negative 32 feet per second squared approximately. Negative 32 feet per second squared, which is what we're going to use whenever we have feet. If we had meters, they were using the negative 9.8, which is true if we had meters, which we don't. Wait, kiddos, hold on. So this is a constant acceleration problem. So we can cheat and use our formulas from the page before. What? Go team! What are they asking for in letter A? Hey, is there a formula that we just wrote down a little bit ago that I'm not making you memorize, but we can cheat and use in homework? Yes. Tell me what it is. Position equals 1/2 acceleration, which is negative 32 times squared, plus, no, v sub naught t, initial velocity time. You guys know where I'm getting this from, right? We just wrote that formula? Okay. V sub naught, wait a minute, am I right to say that initial velocity is positive 64 if gravity is negative 32 feet per second? Yes, why? The ball is being thrown up. That's positive velocity, but gravity is pulling it down. That's negative acceleration. Does that make sense? Kind of? Okay. Plus, initial velocity is 64 feet per second times time. Plus, initial position is 80. What? Go team. Now, could we have integrated and plugged all sorts of stuff in? Yes. But maybe we can shortcut this every now and then like a physics person would do, yeah? Yeah, kid. Okay, hold on, let me show you something. That's actually like a scientific fact. So in your directions, you're going to be given, don't write this down yet, but you're going to be given this as a fact to use. Does that make sense? So I gave you the fact. Yeah. We'll come back to that example in just a second. Here we go. So don't worry, like we could do some different like physics. Oh no, wrong button, hold on. There we go. In a physics lab, you might try to discover gravity in the sense of approximately like doing a motion lab, but with us, we'll just say, cool, we'll use it. All right, letter B. What's the second part of the question?
When does the ball?
When. What variable is when? Time. Find time for hit the ground. When position is 0. Does that make sense, guys? Part of this is learning to read the problem. Hit the ground where your position is 0. You're on the ground, right? Oh, wait, don't we have an equation for position? Sweet. All we're doing then is setting this whole shabam equal to 0. Not cool, kids. Unless this is an easily factorable. Is that grammatically correct? I don't know. Problem, they would let you use a calculator and you could graph. Do you guys remember how to do this in your graphing calculator? You could graph this as your y1. And then you could find the zeros, right? Now, if they're asking for a real-life problem and they're not talking about like one certain point in time with, I don't know, like a previous point in time and a later point in time, if it's a normal problem, we're just going to choose the positive time, assuming time starts at 0. Every now and then maybe motion has been happening and initial time is some part way into the motion problem, but usually time equals 0 is the beginning of the scenario, so there's no negative time anyway. Has anybody tried to factor? Does it work out nicely? Aha, because we can pull out a negative 16, and what do we get?
G squared plus
Minus. Oh, easy cheesy. So then we end up with negative 16t minus 5 times t plus 1. So t is equal to, remember this is all equal to 0. T is equal to negative 1 and positive 5. But if we're talking about a normal struggle, that comma is not working out so hot. Whatever. If we're talking about a normal problem, what's our answer? The positive answer. So t is equal to 5, and in physics you always have to put units. In any word problem where there are units, we have to put it. T equals 5 seconds. 5 seconds later, it's on the ground. Yeah.
Why did you choose the positive answer?
Oh, because in a motion problem, t equals 0 unless they say otherwise. T equals 0 is the beginning, so we never go before the beginning. Does that make sense? So only positive answers. All right, what else do we got? Ooh, another example. With what initial velocity? Ooh, can't we start writing stuff like find? With what initial velocity must an object be thrown upward from ground level to reach the top of the Washington Monument, which has a height of approximately 555 feet? With what initial velocity must an object be thrown, or maybe we should say shot? Thrown? Really? In order to reach the height. Wait, what's height? Position. Initial position? Nah, what's initial position, guys? Yeah, it's from ground level. Is there anything else we know? Hold on. These are my givens, not my find, right?
Ground level.
Ground level, so initial position is 0. Acceleration, exactly. This is an up-down problem, which means I can use gravity, and didn't they tell it to me in the beginning? This is a feet problem. Washington Monument actually isn't that high, but at the pre-cal last year, we had like a comparison of, I forget what different monuments we had. Anyway. I the Sphinx. The Sphinx isn't very high even. Kind of small, anticlimactic. Missing a nose. Anyway, so how do we put all this stuff into a problem? Wait, don't we have an equation for position given a constant acceleration? Why don't we just plug in what we know? Does that sound good? So we can say x of t is a specific 555 is what they're asking us to set it equal to. We have 1/2 acceleration, which is negative 32 t squared. Sorry, plus initial velocity. Uh-oh, I don't know that guy. Plus initial position. Oh, that's easy. Wait a minute, how do I solve? I only have one. I'm only looking for one, and I have two variables. I only have one equation. I could get v of t alone, but the problem is, I still have a t. What if we make, because they just want like the minimum initial velocity, which means that the highest you throw it is 555 and then it comes down. So that would be at the top of the motion, right? What's going on at the top of something's motion? It's a maximum, calculusly speaking, mathematically speaking. What's going on to the rate or the slope at the top of a parabolic curve? Ooh! Physically speaking, in between going up and going down, every object has to momentarily stop. So we know at this point the derivative of position, which is the same thing as velocity, is equal to 0. Wait a minute, why am I making a big deal about velocity being 0? Don't we have an equation for velocity? So can't we set velocity equal to 0? And we have a of t, which we already know is negative 32, t plus initial velocity. Mathematically speaking, if I have two equations and two unknowns, can I solve that, guys? Yeah, I can. And since we're trying to solve for initial velocity, I don't know, it's kind of up to you guys. Do you want to solve for t or solve for v sub naught? V sub naught. Alright, so v sub naught is equal to 32t, because we're just adding it to the other side. Once we have this shabam, we can go ahead and plug it into this shabam, mathematically speaking, and we have 555 equals negative 16 t squared plus, plugging in v sub naught, 32t times t plus 0 goes away, which means 555. Oh, did I not put in my negative? Oh, wait. But we solve for v sub naught, which means we add it to the other side. Does that make sense? There we go. So when we plug it in, it's just a positive 32t plus 0 goes away. So we have negative 16t squared plus 32t squared ends up being 16t squared, combining like terms. So t is equal to the positive, remember we only choose positive, square root of 555 over 16. You guys see me doing my algebra? But who did I want? V sub naught. So what do I do with this t? Plug him in where? Oh, the easy equation, right? So v sub naught is equal to positive 32 square root of, wait, don't we know the square root of 16? Square root of 555 all over 4, which is 8 square root of 555. Could there be a perfect square in there? Has anybody checked it? 111? Ew, gross, no. Anything going to 111? I don't think so. Wait, what are my units? Oh no, it's a physics problem. Velocity. Ooh, how fast? Ooh, like miles per hour. Except in this one, feet per second. It's important to remember what kinds of units go with acceleration, go with velocity, and go with position. How bad was that? Dun, 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 dun. Maybe not too bad. Uno más. Doing all right, but I want to at least let you guys know what to do in your motion packet for tomorrow. That's why we're going kind of fast. It's in the video. Feel free, go check it out. And this will help you with homework, because homework number 26 is basically these types of problems. I gave you odds, I gave you evens. Odds are in CalcChat. If your sub lets you, I totally don't mind you guys opening up CalcChat to have it as a reference tomorrow. Sound good? Oh, bring your books tomorrow. I should write it. I already turned it in. Okay. Kids can use CalcChat on phones. Okay. Putting it as a mental note. A projectile is launched vertically upward from ground level. So many clues in that phrase. With an initial velocity of 33 meters per second. Whoa, whoa, whoa. Meters. Do you guys see what changed in the directions? Now we're using gravity in terms of meters. It's a little bit different. I know things like initial position is, help me out, 0, because it starts from the ground. Good. What's initial velocity? Which backs up its claim that it was shot upwards, right? Find the velocity at 3 and 5. Wait, velocity. In order to find the velocity, I need a velocity function. Well, how do I do that? I make one. How? Using the ones in our notes, which is you guys find it? A sub naught t plus b sub naught. Did you find it? So a sub naught, negative 9.8 this time. T plus b sub naught, which is 33. How do I finish this problem? We'll find v of 3 and find v of 5. Plug it in, plug it in. What are the units going to be?
Meters.
Yeah, not feet. We got to make sure that we're keeping track of what's going on, right? Is that cool if I just say you guys can plug in? Letter B. How high will the projectile rise? Well, think about it. It's being shot up. Everything that goes up must come down as long as it's still in our atmosphere. So therefore, what happens at the top? We already talked about it. What equals 0? Velocity, not position, because position, it's a certain height off the ground, right? But velocity equals 0 at the top. So what are we going to do for letter B? Set our velocity function equal to 0, and then, can I trust you guys can solve this simple algebraic problem? Yes. And what's time going to be measured in? Seconds. Letter C, find the speed of the projectile when it hits the ground. What do I know about hits the ground? What 0? Position is 0. Wait, I just said of 0. My bad. Position, sorry. And then what do I know about speed? So I can't find speed until I figure out the whole hit the ground clue, right? So the hit the ground clue, what am I going to do? Take my position function. Can we find a position function given our other clues? We're going to solve for t or solve for time. And once I solve for time, what am I going to do? Plug it into velocity and take the absolute value. Final units are going to be measured in, once again, meters per second. All right, kiddos, these are all the examples that I had for homework number 26. These are all the examples I had for homework number 26, section 4.1b, which you're working on tomorrow. But wait, I said I was going to tell you in your motion packet what to star to try tomorrow. Now, hold on. Where do you think I want you to start tomorrow? Just listen up. I want you to start tomorrow on homework number 26. It's the first thing written. It's the first thing we need to get done in the book. Start with that. Extra time. I want you guys to go ahead and star example 1. Sorry, worksheet number 2. Did I say that wrong earlier? Example 1, example 2, and example 3. But I want you to work backwards. Starting at example 3 because I think he's the easiest. Starting at example 3 because I think he's the easiest. And I bet we'll work together a bit on example 1 and 2 on Tuesday. So, what do you need to get done by tomorrow and a 3-day weekend? Homework number 26, example number 3, and just try to get as far as you can on 1 and 2. Sound good? Bye guys, I'll see you later. Bridget, you want where we were before, right? There you go, Kay. Is that it? Okay. Bye, cool kids. See you later.
I wore them and I was like, I'm gonna hurt myself outright.
Yeah.
Do you know who Andrew Garfield is?